Let's keep up with some probability, folks. In this section, we are going to talk about the addition rule and complements, two big concepts that we're working with in terms of probability. All right? Okay, so if two events are disjoint, of course, we're going to be doing some vocabulary because that's how we roll, right? I'll make this bigger so we can see it better. If two events are disjoint or mutually exclusive, so those are synonymous, that it means that they have no outcomes in common. And, oh my, something a little wonky donkey there, didn't it? So think about this for a second. Disjoint, nothing that joins them together. Mutually exclusive, nothing in common, right? So look at the words themselves, and that helps define what is actually going on. Disjoint or mutually exclusive mean the same thing with no outcomes in common. So let's look at the addition rule for disjoint events, meaning there's nothing in common. All right. So if E and F are disjoint or mutually exclusive, remember we said those were the same thing, then the probability of E or F is equal to the probability of E plus the probability of F. Now I'm getting ready to drop the bomb right here. The word or is the addition rule. That's the key. The word or is the addition rule. We are going to do another rule, the multiplication rule, all right, that we're going to be looking at. And then we'll talk about that at a different time. But for right now, you need to focus right here on the addition rule. And then the word or, this tiny little two-letter word is what's going to show up. And this two-letter word is going to tell you how to work with it. So anytime you see the word or, automatically in probability, you need to be thinking of addition. Okay, that's a big deal, so that's why I spent a little bit of back and forth on it. So, I don't know, put bells on there, highlight it, whatever you need to do to remember that part of it, because that's a big deal. All right, let's keep on keeping on here. Our number system consists, yikes, of the digits 0 to 9. Because we do not write numbers such as 12 as 0, 1, 2, the first significant digit in any number must be 1, 2, 3, 4, 5, 6, 7, 8, or 9. We may think that each digit appears with equal frequency so that each digit has a 1/9 probability of being the first significant digit, but that's not true. In 1881, Simon Newcomb discovered that digits do not occur with equal frequency. The physicist Frank Binford discovered the same result in 1938. So there is validity there, right? After studying lots and lots of data, he assigned probabilities of occurrence for each of the first digits as shown in Table 5. The probability model is known as Binford's law and plays a major role in identifying fraudulent data on tax returns and accounting books. All right? Verify that Binford's law is a probability model. So think about what we did last section. If we want to find a probability model, there's two criteria associated with that. Do you remember what they are? What was the first one? Yes, all probabilities have to be between 0 and 1 inclusive. So we've got 0 is less than or equal to the probability of the event, which is less than or equal to 1. Remember, inclusive. So between 0 and 1 inclusive. Does that hold true for these values? Yes, none of them are negative, so they know it's not back here. And none of them are greater than 1, so we know that that's also happening. Sweet, so yes, that is true. What's the second criteria? They all add up to 1. Good. So I'm going to sum my probabilities to equal 1. Right? Okay, so do that on your calculator. Add all those up. If you add all those together, what do they equal? Knock that out here real quick. Yes, they all equal 1. Yes. They all add up to 1. They all add up to 1. So yes. So is this a probability model? Yeah, because it meets both of those criteria. Sweet. Okay. Now I'm going to scoot this up so we can see the data better. Use Benford's law, which is just this information in this table right here, to determine the probability that a randomly selected digit is 1. What's that word right there? Or 2. And what did we just say whenever you see that 2 little letter word? What do you think of? You think of addition. Yes, okay. So let's do it right now. The probability of 1 or 2 is the probability of 1 plus the probability of 2, because that little 2-letter word means addition. So look at what we've got here. 1 is 0.301. 2 is 0.176. Okay, well, plug those into your calculator and add those together. Well, we don't even need to be 0.477. That is a probability of 1 or 2. Again, I want to make a huge impact. This word or is the addition rule. Or is the addition rule. Okay. Then we're going to use Benford's law to determine the probability that a randomly selected first digit is at least 6. So what does that tell you? 6, 7, 8, or 9. Yes. So we've got all of them. So this is the probability that we have 6 or 7 or 8 or 9. So add them up. The word or adds us up. The probability of 8 and the probability of 9. If I'm given all these different probabilities, then whenever we look at that. Okay, so 0.067, 0.058, 0.051, and 0.046. Okay, get your calculator out. Add all those up. Tell me what you get. 0.222. Nice. Spot on. The key to this is as soon as you see probability, it always has to meet the 2 criteria. Whenever it says the word or, you're going to do addition. Addition takes care of that word or. Okay. Let's do this. Hope I got a thing on my screen. There we go. All right, suppose that a single card is selected from a 52 standard deck, such as the one shown below. Now, I've done this class for a while now, and it took me a while. I didn't realize at first that not everybody knows what playing cards look like. So a deck of cards. So there are 52 cards in a deck. There are 4 suits. There are spades, hearts, clubs, and diamonds. Those are the 4 suits. And they go from an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then jack, queen, king. So it's a 1, but the 1 is called an ace. So it's ace to 10, and then jack, queen, king. Depending on the game that you're playing, sometimes the ace is higher than the king. All right. For our intents and purposes, we just want to know what is available for cards. So I put this graphic on there. So if you're not familiar with playing cards, then you can use this graphic so that it helps you. We're just trying to figure out probability. All right. So we want to compute the probability of the event E, which is drawing a king. Anytime I want to do probability, if I'm looking at this, my probability of getting a king is going to be part out of whole. So how many kings are there? 4, right? 4 out of how many total? 52, because there's 52 cards in a deck. All right. So 4 out of 52 would be 1 out of 13. Remember, probability is either a decimal or a fraction. And so I'm just leaving it as a fraction right now. Cool, right? Okay. Compute the probability of the event drawing a king or queen or jack. All right. So the probability of a king or queen or jack. What's the probability of drawing a king? 4 out of 52. What's the probability, or 1/13th, right? We just did that one. What's the probability of drawing a queen? 4 out of 52. What's the probability of drawing a jack? 4 out of 52, right? So you can look at that as you're working through there. I'm going to scoot this up a little bit. I would also be 100% on board knowing this is 1/13th and these all reduced to 1/13th. You could have done 1/13th and add those up 3 times. Your choice, all right? But the word or definitely has to go for the plus sign. All right, so whether you do it this way, and so you end up with 12 over 52, you do need to reduce that to 3 over 13. And then that's going to be your probability. All right? Pretty cool, right? General addition rule. And if you're not familiar with cards, here is your graphic. So keep your notes handy, and so then you can see that if you need to reference it.